this video, I will tell you about types of binary tree. Before discussing about types of binary tree, I want to tell something more about tree data structure. So tree is a non-linear data structure and it is helpful for representing hierarchical data structure. Now what is hierarchy? I will explain you with the help of the example that is organization. In an organization, there are some kind of employees and they have their own designation. See the diagram. Here you can see that it is divided into three parts, that is top management, middle management and first line management. Under top management, first chairman comes, then vice president, then board of directors, then chief executive officer. If chief executive officer face any problem, then he or she will contact with their senior. Similarly, if board of directors face any problem, they will contact with their vice president. If vice president have any problem, they will contact their chairman. There is one more example, which is our system. Our system has some kind of drives like C drive, D drive, and under C drive, D drive we have some folders. And under folders we have some kind of images, some kind of videos, audios and some kind of application programs. So our computer file system also work on tree data structure. There are some linear data structure also like arrays, stack, queue, linked lists, etc. We will continue with the types of binary tree. The first one is full or strict binary tree. In this, all nodes have either 0 or 2 children. You can see in the diagram also, this node have exactly 2 children and this node also have exactly 2 children. Now, if I see this node, then this node has 0 children. So this is fulfilling the property of the full or strict binary tree. If I draw a diagram which is like 7, 2, 3, 1, 5, 9. And I ask you that is this tree is full or strict binary tree? So the answer will be no, because this is not fulfilling the property of full or strict binary tree. In this, tree has only one node, which is not satisfying the property of full or strict binary tree. Okay, in this, every node can have only 0 or 2 children. Now the next one is perfect binary tree. In the case of perfect binary tree, internal nodes have 2 children and all the leaf nodes are on the same level. You can see in this tree also, all the internal nodes have 2 children and the leaf nodes are on the same level. Now, if I draw a tree which is like 7, 2, 1, 5, 3. And I ask you that is this tree is a perfect binary tree? So the answer will be no, because in this all leaf nodes are not at the same level. Okay.
The next one is complete binary tree. All levels are completely filled except possibly the last level, and the last level must have its keys as left as possible. This means that here all levels should be completely filled except the last level, and last level should have its node as left as possible. You can see this tree also. In this, all the levels are completely filled and the last level has its node in the left side. Suppose I draw a tree which is like 7, 2, 3, 1, 5 and 0. And I ask you that is this tree is a complete binary tree? So the answer will be no, because In the last level, this node is present at the right side, and this is violating the property of the complete binary tree because this node should be as left as possible. The next one is degenerate or pathological tree. In this, parent node has exactly one children. You can see in this tree also, this node has only one children, this node also has only one children. Next is a skewed binary tree. In the case of a skewed binary tree, a skewed binary tree is a pathological or degenerate binary tree in which the tree is either dominated by the left node or the right node. There are two types of skewed binary tree, which is left skewed and right skewed. In the case of left skewed, a root node has all its children in the left side only, and in the case of right skewed, a root node can have all its children in the right side only. The next one is balanced binary tree. In the case of balanced binary tree, the difference between the left and right subtree for each node is either 0 or 1. So, for calculating the difference, we first need to know that how we can calculate the height of the binary tree, and for calculating the height of the binary tree, we must know that how we can calculate the height of every node. So first we will see that how we can calculate the height of the node. So for calculating the height of the node, we will use a formula which is number of edges from the root to leaf. So if I want to calculate the height of this node, so we will see its edges from the root. So the number of edges is 1 and 2. So the height of this node will be 2. Similarly, the height of this node will be 2 because there are two number of edges from the root node. The height of this node will be 1, and the height of this node will also be 1 because in this there is only one number of edge from the root. Now we will just see that how we can calculate the height of the root node. So for calculating the height, we always observe longest path, and the longest path is present in the left side. So the height of this node will be 2 only. Now if I want to calculate the height of the complete binary tree, so it will be like number of edges from the longest path from root to leaf. So the longest path is what? This one or this one. So the number of edge between this is 2 plus 1. So 2 plus 1 is equal to 3, which is height of the complete binary tree. Now if I want to calculate the difference between the left and right subtree, so the formula is height of left subtree minus height of right subtree. Okay, so here the height of left subtree is 2 and the height of right subtree is also 2. So 2 minus 2, which is equal to 0. So the difference is what? Difference is 0. Here also 1 minus 1, so the difference is 0. Here the height of the left subtree is what? 2, and the height of the right subtree is what? 1. So the difference is what? 1. So this tree is fulfilling the property of balanced binary tree because in this the difference is what? Either 0 or 1. So that's it for today's video. Thanks a lot.